So today I want to talk about data science in sports, and we'll mostly focus on the NFL, probably because that's where I've done the most work, and also it's my favorite sport to ingest. So a little bit about me. I graduated from the University of Missouri in 2015. I have a master's degree in computer science, and my emphasis was in sports data science. And my thesis, I chose to go the thesis route instead of the project route. And it was written in improving the NFL draft accuracy. The overarching goal of my thesis was to show that you can use machine learning to actually pick players better than existing NFL GMs do. And on another level, it was also built to look for diamond in the rough type players who may have a lot of good qualities that may not have had a lot of exposure because they play at a smaller school, or they play at a Division II school. They're not even on anyone's radar, or they're maybe short, have some physical attributes that maybe people think might not work well for that player in the NFL. And I actually found a handful of players like that who ended up doing quite well. One of them was Albert Wilson. So anyone here is a Chiefs fan? Chiefs fan, you probably know who Albert Wilson is. He was one of the person my algorithm over and over again said, this is the guy we want to get. And he was an undrafted free agent. Now he signed, last year he signed a very large contract with Miami Dolphins, and he's been a productive player in the NFL. So the goal was to search for diamonds in the rough and just do an overall better job than NFL GMs did. And if you kind of follow the NFL closely, you'll know that some of the GMs really are not interested in data science. They're not interested in using computation or algorithms to help select players. And oftentimes, NFL GMs are actually a friend to someone who has a lot of money, and it's just a game to them. So teams like the Redskins, who oftentimes spend a lot of money, they have a poor relationship with their owner, who is his last name Snyder. He makes a lot of their decisions for them, but he's not very connected to football. So he makes poor decisions, and that's why oftentimes the Redskins fans are very upset with the decisions they make, the trades they make, etc. However, there are many teams in the NFL currently that are starting to open this door. And maybe I could take it off of that picture so you guys don't have to look at me stick with my tongue out. But many teams in the NFL are starting to open that door and say, hey, let's start taking machine learning and data science seriously. Let's start using these tools to evaluate players and who to bring in. Another thing about sports and data science in general, baseball has been way ahead of the curve on this. So every 3 or 4 years now, you'll hear a new stat being used in baseball, and you're kind of like, well, why am I starting to hear about that? Well, the reason you're starting to hear about that is because that's one of the metrics or the features that baseball GMs and baseball geeks, I guess, are starting to look at. So right now, one of the hot stats is the speed of the ball off the bat. They've started to really look at that, how fast the ball is leaving the player's bat. So that's one analytical piece that they've started to look at to decide who to bring in. I believe if you're a Cardinals fan, Randall Grichuk, the reason he was signed was just for that reason, because he had very good ball speed off his bat. So a little more about me. I do teach Capstone 1 and Capstone 2 in the CS department. Who here is yet to take that class or is going to in the future? Okay, 2, cool. So I'm assuming that most of you are probably from ECE or CS or IT. Where are we coming from? IT, CS, ECE, EE? Mixture of everywhere?
Yeah, there's some people from BU, some IT, some
okay.
ITs. Like it's
cool. We've got a little bit of everything. This is going to be great. So what is data science anyway? So we talked a little bit about it at the introduction. And I stole this from Cal Berkeley. Anyone who's familiar with computer science, one of the favorite things we like to say is don't reinvent the wheel. So why reinvent this process when they already have this existing nicely? So the first thing we're going to talk about is capture. So I really like this 5-step process that Cal Berkeley put forward. It makes a lot of sense. I had not seen it until I decided to start writing these slides 2 days ago. And I really like it. So the first part of data science is your data capture. And I'll be very straightforward with you. Anybody can do this 5-step process if you have the right tools. Like I keep saying, the first step is capture. That's where you get all of your data. You have to find a way to get information, data, whether it's in a SQL database, in a spreadsheet, in a NoSQL database, wherever it is, you need to have your data, and you need to find a way to procure it. Now, a lot of times it takes a lot of elbow grease to do that. There could be situations where you may have to hand enter a lot of data over time, or build a web crawler. So it doesn't matter how you get your data. The first step of any data science project, for the most part, is acquiring data. Then they have this maintenance block that kind of dips down. And that's really handy in industry. Whenever you're doing personal projects like myself, the maintenance is really not as important, except for the second item there, the data cleansing. That is very, very important. The processing is also important, but the way this is kind of built, the data processing and the process are kind of hand in hand. And I'll describe that a little more later. So then you have the processing of the data. That's where you perform your data mining. You may do some clustering or some classification. You may choose what particular items in your data you are trying to predict. And we'll talk a little more on that later as well. Then you go to the analyze part. That's the part where you're going to bust out your big algorithms. That's where you're going to drop your data into one of your machine learning algorithms to try and put out a prediction for some item or field you're trying to discover or predict. The last one is to communicate. Once again, if you're working on a personal project, you can talk to yourself, and you'll see later who I talked to after I had my findings. But that's another important part. And once again, like the maintenance block there, it is mainly geared towards doing data science in industry where you may have management or other people on your team, the public, et cetera, to report to or communicate to. So I felt like this is a really strong 5-step process on just the general idea of what data science is. You gather data, you clean it up, maintain it, pre-process it, get it ready for your algorithms. You do any sort of clustering or classification you need to do before, layer it over your data. Then you need to analyze, run it through your algorithms, and then check out the results and then report it however you need to. So let's talk about something I did shortly after I got out of grad school. And I might have still been in grad school at that point in time. I can't remember. I don't really remember. I remember I did a lot of this work during the summer. So after I got out of grad school, I had a little bit of free time on my hands, and I was trying to figure out what to do now that I'm not actually working on homework or assignments 30 hours a week, or however long it's taking. I had a little bit of free time, and I actually am kind of a continuous learning junkie, or a computer science junkie. Like, I just can't get enough. So instead of most people, how they normally want to spend their summer, either, at the lake or out, at the pool or having a good time, I chose to spend my summer collecting data. And that's why I'm so pale. Anyways, the overarching idea I had after I got out of school was that you could use machine learning to beat the NFL spread. I thought you could do that, and then that would be worth a lot of money. So I started working towards it. So remember that 5-step process beforehand where you have to, where the first step that I brought up was the capture. So how did I capture all of this data to input and be ready to prepare to run my algorithms against? Well, I used 3 things. One of them was Google Sheets. Another thing was Pro Football Reference. They have tons of CSV data that you can just peel from their site and load into a sheet. And then a lot of what Jim Carrey is doing here. Typing in information, just running it through. The part of your machine learning, once you get good at machine learning and data science, the part that's going to take the most time for you is this part. Getting the data ready, preparing it, gathering it, collecting it. This is what's going to take the most time. And eventually I ended up with a huge amount of information like this. And each one of these columns here, let's talk about this real quick because it's kind of an important vocabulary word for later. Each one of these columns you see in this data, no, let me rephrase that. Almost every one of these columns in this data is referred to as a feature. So whenever I'm going and I'm trying to beat the NFL spread, I'm trying to find important data elements that may give insight into areas where I may find an advantage or a hole or a gap where I actually am doing better than they are at evaluating the spread. So for instance, this column here that says off by, or now that it wiggled on me, one of them said off by. What that means is, was that team coming off a bye that week? A 1 means yes, a 0 means no. Next bye, that means, does the team have a bye next week? Are they maybe cashing in a little early, looking forward to going to Cancun or wherever it is they want to go? What's the status of the quarterback? Are they injured or are they benched? What was their status at the beginning of the year? There's also some items in there to kind of denote dates, identifiers to help me know, to help me have a somewhat relational effect so that I can identify it uniquely every single row. So there's items in there as well, which those are not used towards the calculations for good reason. So you end up with a huge pile of data. Next, you need to maintain it. So you see a little magnifying lens there. It's good to go through and QA your data. You can choose a certain percentage. I prefer about 10%. Go through, QA it, check it, and make sure it's good. If you don't have many errors, then you can go ahead and say, I'm going to accept this data. But you need to go through and you need to maintain it. Now, there are many times, I'll tell you, while I was creating my data, that I may have copied something into the wrong row, and I'd have to go find it and flip it around and fix it. So that's all part of the preparation for getting ready to insert this data into your algorithms. So the pre-processing phase, there's a lot of different machine learning algorithms out there. And when you look at these features or these fields at the top of this data, it's almost kind of like whenever you have the data and you're trying to fit it into an algorithm, it's almost kind of like those old Nintendo games where you put the cartridge in and all the pins align and it's able to play the game. So just like your algorithm is needing to have, or just like the Nintendo, the original Nintendo made in 1985 needs to have those pins line up just right for the Nintendo to run, your data needs to have its elements lined up just right for the algorithm to be able to run against your data. So for instance, there's some regression algorithms that will not accept text data. They can't have a text field. So the algorithm we'll discuss first is not like that. For instance, here, game type, there's text in here. What that means is non-divisional home favorite. So that game type, the team playing is a non-divisional home favorite. That's a text field. Naive Bayes can get away with handling text. Some other algorithms can't. There's also another field that's very important, and it's this one, right, if I can find it. There's one that says ATS. So remember earlier I was talking about the features, how there's a ton of features, and almost all of the elements in the data are features. However, there's one element which is different than all the rest. And that is the element in which you are trying to predict upon. That is called the classifier. So in this data somewhere, I have an ATS column, and that simply means against the spread. 1 means they won, they beat the spread that particular game. 0 means they did not. Since I'm trying to predict upon whether or not a team is going to beat the spread, that is my classifier field. So I know for each of these data elements, in this case, this one did beat the spread or this one did not. That's going to be very important. And almost every single machine learning algorithm, every single supervised machine learning algorithm will have a classifier of some kind or a label of some kind. Unsupervised do not, which they're a lot of fun too, and we'll talk about those later. So like I said, you have to have the data finagled in the right way. It has to be able to fit into the algorithm so it can process it. So whenever you're doing the pre-processing, this portion of the steps in the 5-step process that Cal Berkeley gave us, it's important to know beforehand what algorithm you're using. So I kind of skipped a small step at the very beginning during the capture while they're obtaining the data. At that point in time, they're probably going to know, hey, we want to run this against linear regression. We want to run this against logistic regression. Let's try naive Bayes. Let's try deep learning, and let's try neural nets. Let's try those 5. So let's get data ready for those 5 things. Since those are all supervised learning methods, the data is going to be fairly similar because they all need the features and they all need classifiers. Each one of those supervised learning algorithms requires that. The algorithm I chose for this particular example for this particular work was naive Bayes. And we're going to go into naive Bayes in some pretty lengthy detail. So remember, there's 2 types of machine learning. There's supervised and unsupervised. Supervised, you have data for a labeled field that is the actual item you're trying to predict. Whereas unsupervised, you don't know anything, and the algorithm is going to group things for you or cluster things for you. Yeah.
How long was your training set?
My training set for that, I had, let's pull it up. It would have been 80% of whatever the total is. We got to figure out which one it is. Spread algorithm stuff, that sounds professional. So this went from, I think, 2011 to 2016. I can't remember. Hello. Oh, there we go. Oh, this is apples. Okay, so I had 2,561 rows total, of which 80% of that I would have used for training data. And that would have been, what, 80% of that? Gosh, I don't want to think that hard. Anyone want to think that hard? Is that like 1,800 or so, 2,000 or so, somewhere around there? So I had about 2,000, 1,800, 2,000 for my training. Okay, where are we going here? So like I was talking about before, we have the supervised data. So in this particular instance, I have this red box around ATS, which is against the spread. And it's either a 1 or a 0 to denote whether or not they beat it on that particular example. Now, what naive Bayes does, since we chose naive Bayes, we can use prior knowledge to try and predict what may happen in the future. Naive Bayes, once you see it explained, is incredibly intuitive and very, very simple. It'll just click like that. Unfortunately, the example I have is not fitted to this data. It's the same exact example I used in class. I didn't really have a lot of time. I had maybe a day or 2 to prepare these, and I work full time. So it's a little example of what I have in class, but essentially we want to use statistics generated from our data to predict whether or not a new row of information should be a 1 or a 0, meaning a new row of information, whether or not this item is going to beat the spread or not. In this case, 1 means beating the spread, and 0 does not. It means not beating the spread. So naive Bayes algorithm is based on a simplified version of Bayes' theorem. In its simplest description, Bayes' theorem is a statistical approach to handling many levels of statistical occurrence. So kind of a way to explain this is you go outside and the grass is wet. What is the probability that it rained given that the grass is wet? Well, you may find out that it rains 15% of the time in the particular region you're at. So you have 15% chance that it rains. But then you also find out there's a sprinkler in the neighborhood that runs as well. So now you have another element entered into your statistics that can change the effect of the water on the grass based on 2 different statistical outcomes. And you can chain all of these together. You could go back a step further and try to calculate the probability of the rain. You could say, well, the temperature was this yesterday, or the humidity was this, and you can calculate that. Eventually, you can get a huge chain of Bayesian Bayesian statistics to solve. This can become incredibly computationally expensive. Dependent statistical chains like this are very, 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 very messy. So naive Bayes does something incredibly lazy, and they say, well, let's just be as simple as possible. Let's make it not so that everything is dependent upon one another. Let's assume independence across the board. So whenever you assume independence statistically, you end up with a situation, even with naive Bayes, where essentially it's a dice roll. Meaning, if you pick up a dice and you roll a 6, the chance that you're going to get a 6 the next time is 1 in 6. The chance you get a 6 the next time after that is 1 in 6. It's always 1 in 6 no matter what. The chance you roll three sixes in a row, let's not use that. 4 6s in a row is 1 over 6 to the 4th power. So it's just taking the product. Very simple statistical theory that you've all been doing ever since probably elementary school in your heads. So here's the actual formula, the mathematical formula for naive Bayes algorithm. So essentially, it's choosing the maximum argument between two items. So naive Bayes algorithm spits out two values, and the value which is greater is the one which is predicted. So you have all of your data. You evaluate your data, and you apply a percentage, a prior probability to every element of your data, except for your classifier, your field you're trying to predict. Then you multiply all those out. You have a positive case and a negative case. Whichever case is greater, whichever item is larger, is the one you end up choosing as your predictor. So I'm going to go through an example that I do with my students in Capstone 1. So before we get there, I just want to say a few more things about naive Bayes. It's really dependent on pre-calculated statistics. So you have all this data, you need to calculate all of these statistics on your data. So naive Bayes, actually, after you have your pre-calculated statistics, it's very efficient. It runs very fast compared to other machine learning algorithms. That's often why naive Bayes is one of the first machine learning algorithms developers choose to use, because it's simplistic and it's a good base case. It's kind of your vanilla of machine learning. So, like I said, it's easiest to learn this by example, because I could show you this formula and you're not really going to understand how, well, at least I didn't. Let me rephrase it. I never understood how this related to data. You could show me this. I don't know what this X sub I is. None of this stuff made sense to me until I had a friend sit down with me and show me exactly what everything was. So that's exactly what I'm going to do for you here. So in my class in Capstone 1, I do a naive Bayes example, and this is a terrible example to use, but it's good at proving how the algorithm works. So in my class, we talk about this theoretical situation where I'm collecting data on my students, and at the end of the year, I've been teaching Capstone long enough. I don't really want to calculate grades. I'm lazy. I'll just input these few things here and let my naive Bayes predictor decide whether or not the student got above a B. So in this case, we have features of gender, papers submitted, attendances made, whether or not they participated in class, and then here's your classifier, whether or not they got a B or higher. So we were wanting to predict whether or not these students received a B or higher in the class. So the first step is just calculate the prior probabilities needed for the classifications layer in the algorithm. So remember this formula here. It's a crazy formula. We need to calculate prior probabilities. Right here. So this is the probability of a certain class occurring. Meaning, what is the probability that someone got a B or higher, and then what's the probability that they did not? So after looking at my data from years past, I found out that 60% of the class got a B or higher and 40% did not. Now, if you're taking Capstone 2 next semester, do not worry about that, because this is not true. These numbers are not relative. So these are just examples. Okay, next step, we have the probability of C of K given X of I. Okay, what does that mean? The probability of a particular class, a particular data item given a certain class. So in this case, we have the probability of the gender is male given the grade is B or higher. So you can see we have 6 males in total. Wait, that looks like 7. 1, 2, 3, 4. No, 6, 7. Man, did I mess up my numbers here? I've been doing this for 5 years and no one said anything. Probability, oh, sorry, this is wrong. There are 6 yeses. Sometimes I do this backwards. There are 6 yeses, of which 4 of them are males. So the probability that it's a male given that the grade is B or higher is 67%. Probability gender is female given grade is higher. That's 2 out of the 6. And then you look at the negative case and you find out probability that gender is male given the grade is less than 0.75. Sorry, grade is less than B, and that is 0.75. And then probability gender is female given the grade is less than B, and that's 0.25. So does everyone see what's happening with the data? We're using our classifier field, and that is the given field. And then each one of these elements over here has a statistic applied to it based on the given probability. Yes.
So the XI is the gender.
Yes.
And the CK is the field.
Yes. Yes. So X sub I is this particular gender, and C of K in this case is yes, but it could be no. So typically there could be actually 8 or 9 or 3 or 4 potential classes that it could fall under. So you can have more than just 2, but 2 is the simplest way to explain it. So we go through and we're calculating these probabilities. We do the same thing for every element. So the probability that they got a B or higher given that they submitted 3 papers is 0.83%. 2 papers, 17%. 1 paper, not going to happen, 0. Lower than B, 3 papers, 0. So everyone who submitted 3 papers got higher than a B. 2 papers, half of them, and 1 paper, half of them. Do the same thing, continuing going through your X sub I. This might be X sub 3, since we're on the 3rd datum element. And you just continue through. Okay, so now that we've calculated all of these prior probabilities, and I'm feeling lazy, I'm running late on time, and I've got all these students I have to grade, so I'm just going to plop them in my spreadsheet, and I only have 2 students this class, so I must be like phenomenally lazy that I won't even grade these 2. But I have these 2 students that come in, and one's a female. She submitted 2 papers, 4 attendances made, and she participated in class. She did not participate in class. Next one's a male. They submitted 2 papers. They made 3 attendances, and they also did not participate in class. I don't know what I'm doing wrong. No one will participate. So we have our prior probabilities, and we also have our given probabilities. And remember, there's 2 cases. There's the positive case and the negative case. So the probability that you will get a B or greater given that you are a female is 33%. The probability that you will get a B or worse, or sorry, worse than a B, is 25%. And the same goes for each of these. So you have 2 cases, 2 sets of data. And remember, the algorithm is going to multiply all of these across each other and choose the case that is larger. So the argmax predicts the one that is larger. So we go through here and we do all the calculations for the female student. And like I said, we have these 2 components here, which these are just products. And we multiply them all out, just like you would with the dice. It's almost the exact same concept. And then you have to choose the argmax. So whichever one is more likely to happen is the one you predict. So in this case, you're going to select the 0.0094, which is, I believe, the negative case, right? We're going to predict that the female student will get a grade lower than a B. Sorry about that. Okay, do the same thing for the boy, and he also has a much larger number over here on the predictor for the negative case, or for this particular case. And I'm also going to predict that this student will get a grade lower than a B. Now, when I actually look at my data, I finally took enough heat from the students and they made me actually grade their papers. It turns out that my accuracy is only 50% because the female did get a B or higher, and the male did not, while I picked them both to get lower than a B. So my algorithm is only 50% accurate. So now the question is, how do I improve on this? How can I make this better? How can I finally get to my dream where I can just be lazy and never grade anything ever again? Anyone have any suggestions on things yeah?
More features or more training and hopefully it doesn't overfit.
Yep. So add more data. Add new good features and then remove bad features. So in the example I have for the class, I removed the gender column because, quite frankly, what does gender have to do with your grades? It doesn't make any sense. And I also added this other field, which is actually apparently very important as far as whether or not the student gets a B or higher in the class.
Something.
In this case, I would say, oh gosh, no, we're not going that far. we're not stepping that way. You're funny. I mean, that might be one of the funniest things I've heard in a while. Yeah, so it turns out that you have a 100% chance of getting a B or higher if you bribe me. So we brought new data in, and it's able to make my predictor better. Is that clear how that works? So like I was saying before, obtain more data, add new good features, and then remove bad features. So one way you can identify good features, or at least kind of hope to get your foot in the door, is you can run a correlation coefficient against some data to see how correlated the two are. That's one way you could do that up front, and it's very simple to do. I mean, there's calculators online that will calculate correlation for you, and MATLAB probably has one. In fact, I wrote this in MATLAB. No, I wrote it in R, sorry. I didn't want to pay for MATLAB. So back to the gambling. Remember we were talking about the gambling data? So the algorithm, it was not quite as successful as I was hoping. It turns out that people in Vegas who get paid, hundreds of thousands of dollars actually know what they're doing. And I was able to get about 50% accuracy with multiple features, which is beating the spread technically. They say you need about 52.7%. To make money, but you need to have a ton of money to make money at that rate. So the more you make, the more you have, the more you can make with something like this. I don't have a ton of money on hand, so I didn't make a ton of money with it. But interestingly enough, there's one feature I found that when I ran it through the algorithm independently, it had the highest accuracy, even whenever I was using multiple features. And that one field was the score of the last game. So think about football, and think about public perception, and think about Twitter and, social media, everything. Whenever the Browns go to, say they go to some meddling team, like they go to Cincinnati. I'm sorry if you're a Bengals fan, I apologize. And they just get their ass kicked by 24 points. At that point in time, the public sentiment around that team is very negative. And Vegas plays on that. At least this is my hypothesis. To understand, this is an untested hypothesis I've generated here. But I believe that Vegas plays on that human emotion and that human feeling where, oh, man, they're terrible. They just got killed last week. When the truth of the matter is it's much more complicated than that. And teams match up with each other differently week in, week out. Team might get embarrassed that they lost hugely and then play better the next week. But that was the best qualifier, best data field for predicting the spread the next week. So if you like to gamble, go look and see what happened last week. And if the team either blew out the other team or they got killed, you might want to bet against them. Or you want to bet against the team that blew out the other team, and then you want to bet for the team that got blown out. And it's probably because the Vegas is playing a little bit of public perception there. Okay, so unfortunately I didn't have anyone to communicate my results to that were very interesting, so I just told my cat instead. I had to follow procedure, and I wasn't not going to do that. So other supervised learning algorithms, you have linear regression, logistic regression, neural nets, and deep learning. And one very common theme about each one of these algorithms is that they use a weight vector. So let's maybe I've got one coming up. Okay, yeah, so we have some data here. Now this is only, really a 2D data plot. So we have this weight vector here. Now, naive Bayes is a little different in that it will use a lot of pre-calculated probabilities. Machine learning algorithms that use weight vectors, they do calculate these weights as they go along, but it's not the same as naive Bayes where you can use a product. Essentially, what the majority of supervised learning algorithms like linear regression, logistic regression, neural nets, et cetera, that use a weight vector are doing, they're using that weight vector to create a line to separate items in space. So we have this 2x2 data, and 2x2 data looks great on a 2x2 graph. But our question that we're trying to solve with this is, we want to be able to predict which of these players are running backs and which of these players are wide receivers. Just looking at the rushing attempts and the receptions. This is a very simple example. So we plot them. Now, this is a two-dimensional plot. But in computer science, you can have nth dimensional spaces. So let's think about that for a little bit. This is receptions on the left-hand side, rush attempts on the right, or on the bottom. So your y-axis is receptions, x-axis is rush attempts. Well, what happens if you put touchdowns in there, or receiving touchdowns in there? Now you have a z-axis. Well, you can add another element in there. Then you would have a z prime axis, or whatever letter you want to choose. You can use a German S set if you wanted to. But the thing is that every instance of linear regression and logistic regression are the same in that they just want to create a separating hyperplane. Meaning we are looking for a line to draw through this and saying everything on this side of the line is classified as X, everything on the other side of the line is classified as Y. So whenever you run regression algorithms, the goal is to create a separating hyperplane. I love that word, hyperplane, hyperplane, hyperplane. It's just a lot of fun to say. And it's also very cool to think about, nth dimensions and about how you think about a three-dimensional graph and trying to make a curve. So probably a lot of you have taken calculus, and you're always trying to find a fitted curve to underneath a certain line and all that good stuff. It's essentially the same thing. You're trying to find a fitted curve in space where you can separate two classes of data. And you want to do that with as much accuracy as possible. So for instance, your linear regression algorithm, since it's linear regression, you're going to use a linear line. Makes sense, right? So you may start off with your weight vector being applied to your data such that the line starts off like this. Yes?
Other property of the wave vector, like sum of the W's.
So actually, there's a sigmoid function in there, and what it does is it creates a value between 0 and 1. Fantastic question. I'm glad you brought that up. So I believe it's something like 1 over 1 plus e to the, I think, I can't remember off the top of my head. I'd have to pull up that formula to look at it. But essentially, those weight vectors are values between 0 and 1. And there's usually a sigmoid function that controls that, or any other type of step function that you may prefer.
Oh, it goes.
Yes. Yeah. So you may start off with your separating hyperplane initially looking something like this. Now, we all know the wide receivers are on the left-hand side because they have all the receptions, and the running backs are on the wide receivers on the left-hand side because they have all the receptions. The running backs are on the right-hand side because they have all the rush attempts. So this hyperplane is not doing its job. Now, the way linear regression and logistic regression works is it goes through all of your data. And using those weights from before, it adjusts your slope of your line. So each one of these weights adjusts your slopes when it's applied to the data element. So the weight vector would be multiplied against the rush attempts, and the reception would be multiplied against the rush attempts. We're not going to get that far. Really, the most important thing I want to tell you about is that both linear regression and logistic regression are reward and punishment type algorithms. So what that means is if you have an element, say that in this case, say you want, you're still working on your hyperplane and you see that this item doesn't belong in this class up here. These items belong up here. This item does not. So this algorithm will have characterizations for the line. So above the line, it's going to characterize as wide receivers. Below the line, it wants to characterize as running backs. When the algorithm comes across a bad case, it punishes the line and moves it. If it comes across the positive case, it rewards the line a little bit and moves it a little bit closer to it. So it's constantly pushing and pulling and adjusting this line as it goes through the algorithm, trying to seek for a perfect hyperplane. So this is another part of supervised data. You can go through here, and how you're setting the line is by checking those labeled fields. So you go in here and you find out that this player here, oh crap, they're way above the line. This isn't good. We need to reset it. We're going to punish the algorithm. We're going to punish this particular portion. We're going to punish these particular weights and drop the slope or raise it, just depending on which direction it needs to go. So as you see, as the algorithm goes through every single line of data, it continues to modify the line. And slowly over time, the line continues to change. It continues to use those labels and reward or punish it accordingly. And then finally, you have separated data. So you've eventually created your hyperplane. So then you have a new player that comes in, and you've already created all of your weight vectors. You already have your weight vectors finished. Whenever a new player comes in, it's going to take the elements of their data, 3 and 81, multiply it against that weight vector. Wait, sorry, that's not true. This is actually a little bit different. This is going to take the 3 and the 81 and it's just going to be plotted. The weight vector already exists. Since you already had all your calculations run, you already have those values. That vector is already set. So you bring in new data and you plot it. So say if you want to, this is actually whenever you're using your algorithm. So say you've already trained it to this point, you've trained this vector to be this slope. Or if you train this line to be this slope. You bring in new information, Jarvis Landry comes in, and his point is actually, where are we going here? This is going the wrong way. Okay, sorry about that. So Jarvis Landry comes in and his dot's right there. He immediately is classified as a wide receiver because he's on the other side of that hyperplane. And graphically speaking, the biggest difference between linear regression and logistic regression is the line follows a log curve. And you use logarithms instead of typical slope. You also have neural networks. These are a lot more heavy, but they also use weight vectors. Now, what time is it? Okay, so it's almost 3. So I'm actually not going to spend too much on this. We only have 8 minutes left. But same theory. There are weight vectors applied to the data, and they are calculated and adjusted. The neural nets are a little different in that they push data through. They push inputs through. There's a lot of calculations going on. Output layer comes back, and it may be an unsuccessful attempt. So then there's what's called backpropagation. This is, if you ever get to code a neural net, this will be the most pain you will feel in a long time. Basically, what backpropagation does is it goes through and it readjusts every single one of these points and every single one of these weights so that it's updated mathematically to adjust for the outcome that happened here. It may reward or it may punish depending on whether or not the outcome desired was good. So over the years, I've had students who have actually used feed-forward neural nets to do something like this, where you have a Mario game and they train a neural net to learn how to beat the game, or at least get as far as they can through the game. So you see all these crazy lines going everywhere, and you see the buttons on the right. Those buttons on the right, that's your output layer. So the input layer is that image on the left. So you see that box going over there? That is a state space. So if you're ever talking about artificial intelligence or many things, many times whenever you're doing AI or machine learning, you need to set up a state space so that your algorithm can interpret what's going on. So the left area is your map, and that is the state space that the game's identifying. And I think it has black dots for enemies. So the game's going through, and the input is this grid. And then the neural net is training itself and learning over time which outputs to offer based on the inputs it's given. and it continues to process. So for every input it gets, it has a new output. So every time he's moving to the right, there's new inputs. And then you see this line up top that's referring to the fitness. So also with feed-forward neural nets and mini neural nets, depending on how you configure them, they're looking for a fitness as well. So in this case, the fitness is simply, can anyone see what it is? It's just how far right he's moved, how far right Mario has moved. So that's the fitness, and that's what they're looking for. The entire thing that this neural net's trying to solve is moving to the right. It's taking the input from the game, the state space of the game, using neural nets, providing output, which are button presses, and Mario's moving around, and he's beating it. So we've talked about supervised learning for a really long time, and let's talk about unsupervised learning. So this is where we don't have labels. For instance, say actually, I'm just going to, probably the best way to describe this is from the example that we have. But essentially, unsupervised learning is doing grouping. It's doing clustering. It's not finding a particular labeled field or a particular classifier. It's actually classifying them itself. So here's an example. You may have some data, and depending on the clustering algorithm, this one chose to use 3 different colors. So you can also set clustering algorithms to be different. You could choose to cluster over 4 different items. You can choose to cluster over 5. You can choose to cluster based on distance, which the majority of clustering algorithms are heavy on distance formula. So they're really distance-based, or a kind of a state relational based where they are paying attention to who their neighbors are, and then they're grabbing X nearest neighbors. There's actually a clustering algorithm called K nearest neighbors. So maybe I should have called it K nearest neighbors. So I had a group of students who, to kind of give an idea of what you can do with the clustering algorithm, I had this idea where maybe if you assigned like a type to an NFL team. So think about Pokemon. You could have certain types of Pokemon where one team, or where one Pokemon is weak against another Pokemon, another Pokemon is strong against it. So you've got like a fire type Pokemon going up against an ice type Pokemon. Well, the fire type guy is going to win. So my idea was you maybe could assign types to NFL teams, of which these particular types of teams have advantages over other teams. For instance, I always wondered why the Chiefs did so well against the Patriots with Alex Smith, but then they were terrible against the Steelers also with Alex Smith. But then the Patriots would go and they would just destroy the Steelers. So it never made any sense to me. So I thought maybe there was some type at play. And what these groups did is they took a number of statistics of the teams and they clustered them. And that's how they generated their types. So they said, this is a pass-heavy type. This is this type. They had several types. I think they had 8 types before it was all said and done. And they were able to get about a 6% boost in their predictive analysis for whether or not a team would win a game when they added that into their algorithms. So they did got a boost by trying to type the football teams and seeing if they had certain advantages against one another just because of what type of team they are. Okay, so any questions? We covered a lot of crazy stuff. Was it? Yeah, go ahead.
That you were taking was the Excel files and Google Excel.
Yeah.
Excel file. Did you find them? You collect the data from some website and you load it and you modify it.
Mm-hmm. Yeah. So then you can explode data too. So you may have 2 data elements that mean 2 different things, but combined, they actually become something useful. So if you do go further down the road into data science, having a keen eye for that kind of stuff is really important. And I was told something a long time ago by a machine learning teacher, and they were really right. Machine learning is more of an art than it is as a pure science, because you kind of have to sense and feel things. You have to know where to pull information in. you can run correlation coefficients all day long, but no one's going to tell you to dream up this one particular data field that comes out of left field that is very helpful. So that's why it's sort of a mixture of art and science at the same time. Was it useful? Was it bad? Do I need to improve it? Was it interesting? Oh yeah. Hey.
So with that linear regression one, like when you added a new data point, like Jarvis Landry, I think, for example, you continue to train the algorithm based on it. Like if they get it correct, this is like a
so if you've trained your data set and say it's working well, you're happy with your accuracy, you would just leave it. But if you had a Jarvis Landry come in and he was in the wrong place, he was classified incorrectly, then you would want to probably run it through again and see if you can't improve your accuracy. And we could use the same methods that we talked about before, where you could add new data, remove bad features, do different things to try to improve that accuracy. Okay, cool.
Thank you.
Yeah.
Hi, everyone. Yes.
You do take it out.
Yeah. Oh, well, you didn't have to give me anything. Chocolate? Are you kidding me? Right on.
I'm happy you're excited about that.
Yeah, I get excited about chocolate.
I'll remember that when I'm feeling really bad.
Okay, yeah.
Yeah, he told his brides have a 100% correlation in grades, so there you go.
Interesting. Good to know. Good to know, because I definitely still have not emailed in my picture. I'm just being honest.
That's a good one. Yeah, for the part that I saw, it was really, really good. I think she's learning right now. It's kind of hard to follow
yeah,
it
it's
sometimes
fine.
when she's doing it, so it just throws that big equation in more and you
Yeah.
explain it. So it's actually like really.
I'm glad I can help you.
Yeah.
Here, yeah, go to that one day of 5. Sorry, here.
No, you're good. You're good.
You say it was 6% is what you need to, or Jamie, is it auto percentage you need to have?
52.7%.
Yeah, if you hit present.
Yeah, because they
Auto
have a
play.
2.7% market.
And he's
Yeah.
just none.
But you
Oh, wait, let
need
me-
a ton of money to make, like, that's to make
Yeah.
a penny.